Hi, my name is Tejashwini Nagraj. Today I am presenting about deep learning with long short-term memory for time series prediction. Now we are seeing about the main theme of the paper. The paper explores how long short-term memory networks, a type of recurrent neural networks (RNN), can be effectively used for time series forecasting. It emphasizes the ability of LSTMs to capture long-term dependencies which are often lost in traditional RNNs and statistical methods. It showcases the superiority of deep learning in modeling complex, nonlinear temporal patterns compared to classical approaches like SVM, etc. And now we are seeing about the introduction of the paper, where the time series data are sequences of data points recorded over time. Example, temperature, stock prices, energy consumption. And classical models like SVM, linear regression, or ARIMA are limited by assumptions of linearity and short-term memory. Deep learning models, especially LSTM, learn temporal dependencies from data without handicraft features. The paper aims to demonstrate the performance of the reliability of LSTM in time series forecasting applications. And now we are seeing the key concepts of the paper where it is divided like time series, RNNs, vanishing gradient problem, and LSTM. The time series data recorded at successive time intervals, where RNNs neural networks with loops allowing information to persist. And the vanishing gradient problem, the difficulty in learning long range dependencies due to gradient decay. And the LSTM, an enhanced RNN model designed to retain information over long time periods using memory cells and gates. And now we are seeing about the system model, where the system model is given by input and processing and the output. In input, time series data normalized between 0 and 1. In the processing, sequences are created using a sliding window technique. These sequences are fed into stacked LSTM layers. Each LSTM cells processes temporal dependencies and learns a latent representation. In the output, a predicted value representing the next time step in the sequence. And here we are seeing about the system architecture, where you can see it is divided like three-tier architecture. In the next section we are going to know more about the system architecture. Here we can see that architecture overview, where there is input layer, LSTM layer, and the dense output layer. And the regularization, where the dropout layers used between LSTM layers to prevent overfitting. And the loss functions, mean squared errors, MSE. And the optimizers which they used in this is adaptive learning rate optimization algorithm. And here we are going to know about the equations which they used in this paper, where the LSTM uses gates to control the flow of the information, where it denoted as forget gate, input gate, candidate cell state gate, cell state gate, and output gate, and the hidden state. Here we are going to know about the forget gate, where we have the equation of the forget gate, where it is denoted by the weight factors of and the height and width. It decides what portion of previous cell state should be forgotten. With the they use the sigmoid activation, and here the HT represents to the previous hidden state, and the XT represents to the current input. And now we are seeing about the input gate, where this input gate decides how much new information to be added. And the input gate is denoted as IT and the sigmoid function and the weighting factors too. And now we are seeing about the candidate cell state, where it creates potential new memory content. And the cell state update, where it combines retained old memory and new input. Here we are seeing the cell state is denoted as CT and the waiting factors too. And now we are going to see about the output gate, where the output gate is denoted as OT, where the output gate decides which parts of memory to be output, and the hidden state final output pass to the next time step, where the hidden state is denoted as HT. And here we are seeing the comparison between the LSTM and RC-LSTM in the view of generating process of neural connection. If we observe here, um, the LSTM the LSTM block will get the full connection, and the RC LSTM block will get the random collection from the tires, where we get the state information from the input gate to the LSTM and the RC LSTM. Here we are comparing the features where we are getting the full LSTM to the full connection to the LSTM and random connection to the RC LSTM. And now we are seeing about the methodology which they used is data pre-processing and model configuration, training and validation. Here we can see pre-processing where it normalizes data to 0, 1 using min-max scalar and creates input-output sequence using a rolling or sliding window. And the model configuration is where it uses stack two LSTM layers and add dropout to reduce overfitting, and it added dense layers for final output. The training which they used is use ADAM optimizer where loss mean squared error, and the epochs is 100 and the batch size is 32. The validation is split into train and test set where it evaluates using RMSE and MAE. Now here we can see the main code snippet where they used from Carroll's model they imported sequential model, and from Keras layer they imported LSTM and dense layers. Here we can see that they added the model of LSTM and the dense, and here, model compile where it compiles optimizers as Adam and loss as mean squared error (MSE), and the model fit they used is trains and the epochs and the batch sizes. Here we can see the explanation of the code snippet where written sequences true allows output to be used by the next LSTM layer, and the final dense layer outputs the predicted value, and the compiled with MSE loss and Adam optimizer. Here we can see the algorithm overview where the training algorithm for RC-LSTM follows the standard backpropagation through time (BPTT) approach used in LSTMs with modifications to accommodate the random connectivity structure. This involves updating only the weights of the existing connections, leading to faster computations and reduced memory usage. And here we can see the training and the interface of the paper, where during training, the RC-LSTM model learns to predict future values based on input sequences by adjusting the weights of the randomly connected neurons. Interfaces involves feeding new data into the trained model to generate predictions. The reduced complexity of the RC-LSTM allows for the quicker inference beneficial in real-time scenarios. And now we are going to see about the result where the author evaluated the RC-LSTM model on tasks involving the prediction of traffic and mobile user mobility in telecommunication network. The result demonstrated that RC-LSTM achieved predictive accuracy comparable to traditional LSTMs while significantly reducing computational complexity. This efficiency makes RC-LSTM particularly suitable for applications requiring low latency. Where here we can see the results in the graph form, where this first graph represents the performance of RC-LSTM in terms of RMSE and computing time. And the second graph represents the predicted traffic data versus the actual traffic data, where the ground truth is denoted with red lines and the predicted data is denoted with the blue lines. And the other results we are saying in the bar graph form, where the first graph shows the performance comparison between RC LSTM and the popular models, and the second bar graph shows the prediction accuracy of RC LSTM for different users. Where here we can see this red denotes to the SVR, and the green denotes to the ARIMA, and the blue denotes to the FFNN, and orange LSTM, and the pink RC LSTM, and the rose is LSTM model. Now we are seeing the key findings of the paper, where RC-LSTM effectively captures long short-term dependencies in time series data despite its sparse connectivity. The model achieves a balance between computational efficiency and predictive accuracy. The RC-LSTM is well suited for latency-sensitive applications such as network traffic prediction. And now we are going to the conclusion of the paper, where this study presents RC-LSTM as a viable alternative to traditional LSTMs for time series prediction, offering reduced computational requirement without sacrificing performance. This advancement holds promise for real-time application in telecommunication networks and other domains where efficiency is critical. And and here we can see the citation link of the paper, and that's it for the paper. Thank you.